Morris is CEO of CogniVue. CogniVue is a spin-out from a larger company where it was originally an R&D center, but has now become an independent company developing silicon IP processors and other technology for embedded vision. And CogniVue has, what do we want to say, had some hard-won experience in how to create real-world vision systems that are highly constrained in cost, size, and power, but also have to perform their vision functions robustly. So I asked Simon in September to present on some of that experience, some of the projects that they've done. He did a fantastic job, so we've had him have him come back here for an encore, slightly updated and expanded version of that September presentation. So Simon, please take it away.
Great, thanks, Jeff. So I'm going to talk to you about developing low-power, low-cost, small vision systems from a real-world experience of our company, working with our customers. And it's really actually for engineers who are, say, novices at embedding vision applications, features in their products and looking at doing this, or having just gotten involved in this kind of a project. And really what I'm going to cover is a little bit about, some of it's going to be somewhat commonplace, a little bit about how you go about developing your algorithm from scratch, and so that process that you go through, and then the example of doing a smart camera module with our customers and the challenges that we faced working with our customer to solve their problems for their embedded vision application. And then hopefully at the end, you won't have to learn the lessons we learned. So I'll go through the lessons we learned in the process of helping our customer get to production. So let's start off with the essential steps you follow when you're doing your embedded vision application. You start off typically, if you're innovating and inventing, you're quite often looking at an algorithm development that might be on the PC, or you're working with a partner that might be doing your algorithm development on the PC. Then you start thinking about how you have to optimize that algorithm, not necessarily with any constraints in mind, but you might be just purely looking at optimization on the PC platform or the server. And then you start considering how you're actually going to make it portable, because if it's embedded, when we think of embedded, by the way, we actually really think of it deeply embedded. The applications that we support our customers on are really deeply embedded, so they're usually big power and size constraint issues and cost issues at play. So portable, making it portable, minimizing the algorithm in some way, and then porting to the chip or processor platform that is targeted for the application. Sometimes that's iterative as well, because what you think can work doesn't work, and you have to go and look at something else for your platform. And then ultimately field trials, and this actually was a surprise for us how heavily involved we had to get in the field trial of things to help our customers. A little bit more on the details of the algorithm optimization. So you're usually in floating point, you go to fixed point, there might be some data type optimization. You might be including some algorithm profiling at this stage when you're doing the fixed point conversion. Then you're going to make it embedded friendly, looking at sequential memory references, optimizing the mathematical operations that you're performing, trying to minimize the number of operations you might be doing. Looking at as well how you're using memory or memory usage. If you have a large reliance on large caches, maybe evaluating that if you're not dealing with a cache architecture or you got small caches to work with. And then the deeply embedded platform optimization issues can be down to actually looking at, even today, I know a lot of people like to still want to develop in C, but quite often you have to even look at assembler or algebraic assembler, or in the case of an algorithm being implemented on an FPGA, you're looking at RTL optimization. And you're thinking about pipeline optimization to get the performance you need on that platform, memory management to minimize power consumption. That's really, it's not memory management necessarily from a standpoint of minimizing the amount of memory you want to use, but optimization of the power consumption, where your power quite often is as a result of sloppy data movement in vision. So what our customer wanted, this is the interesting part, and actually customers, because we've actually had multiple customers with the same kind of challenges, And they really wanted to develop a better rear camera for cars. Attractive ASP, they were obviously looking at low cost. In this case, the BOM target was around $35. They needed to de-warp of course, the image coming from the fisheye lens, because it's a 180 degree or 190 degree lens on the backup camera, and they wanted a flat view. They also wanted multiple views. This is actually the easy part. But in any case, that was part of the development. The really difficult part was they wanted to do closest object detection, replicating something like ultrasonic distance zones in the camera itself, not in the dash, not in a separate box, but in the camera module. And they wanted to start off by, of course, being cost concerned. They wanted to use a VGA camera initially. It's actually migrated since then to a 720p camera, usually wide dynamic range for low light sensitivity. And boot up, of course, was really important as well. So the camera had to start and show on the display in less than half a millisecond or half a second. Obviously, that's critical to the person backing up. And of course, as I mentioned before, all this processing, they wanted in the camera module. That was the product, really. It wasn't a separate box with a dumb camera plugged into it. And that concept of the zones is what's shown there. So green, yellow, and red were actually mirrored the zones that are defined in ultrasonic sensors. So our research basically determined, so we did, we actually tried to help the customers by marrying them up with third parties. Initially, that's what we looked for, because we were really bringing the processor platform and not necessarily looking at trying to develop the algorithms. We thought this existed somewhere. It turned out it didn't. So we ended up getting involved with the customer and helping them develop the actual algorithm for doing this distance estimation in a single camera. From the research, we discovered you really need to have two algorithm detectors, one when the car is stationary and one when it's moving. You had to reconstruct a 3D scene in order to calculate the distance, which with a single camera, anybody who's got experience in vision knows that's difficult. And then, of course, the more mundane rear camera functions of doing distortion correction, overlay with the object detection, all done in real time. And the embedded platform required, of course, because it's resource constrained and everything else, you have partitioning of the image processing primitives between whether they map better to a scalar processor in the chip or map better to a vector engine. So looking at that, of course, really greatly simplifying the data structures. And in our case, we started, like a lot of people, from OpenCV. So there were a lot of object classes used in OpenCV that we couldn't use, and we had to create simpler data structures. So really reinvent what you get from OpenCV. And then, of course, account for time dependencies. This was also very challenging because you're resource limited, so you got to balance things out and make sure things can all function at the same time, or function in the right amount of time. So the algorithm validation, too, actually was something we underestimated, which I'll talk about towards this, but you start off with a test database, and you just don't find this on the web, by the way. Most of your vision applications you're developing, you just can't go somewhere and get them. There's an example I'll show you later where you can, but in most cases you can't. So you got to create some sort of test database which you can run on your algorithm on the PC, and usually that means going out to the field and actually just doing video recordings. And then you got to decide what's the truth. What is it that you're looking for? What's a true positive, a false positive, and so on, and define what that is so that you have some consistency as you test your algorithm through the various stages of development. As I said, in some cases you can actually find test databases out there that you can use for your development. So, for instance, in face detection and recognition, there's a Ferret face test database, which actually has hundreds of faces in it. And it's quite often used by developers to prove out their algorithms' robustness. However, it's actually, if you use that database, it isn't necessarily challenging enough for most face detection and recognition, especially if it's something far away. So you have to actually look a bit harder, and quite often when you really get into implementing your vision application, create your own database. Now, in the case of face detection recognition, you can actually go to a much larger database. It's called the Labeled Face in the Wild database, and was created by the University of Massachusetts, and it's got 1,600 persons in it, 13,000 images. You can imagine, though, when you're doing your testing of your algorithm as you're developing it, that can be really time-consuming, testing it against that huge database. So you also have a challenge of figuring out how to do this testing iteratively fast. I won't solve that one for you today, but it's an important part of what you do. So significant times needed really to build this image and video test database. And we found, of course, 3 levels of testing were needed. Assessing by observing the detection of false detection rate over the entire database. Testing on the embedded platform, okay? Checking for bit trueness against the PC version of the algorithm. Validating the test database and comparing the performance against the PC version. Okay, so you're going to test what you've done on the PC, what you've done on the embedded platform, and make sure that you're getting the right it's the same number of true positives and true number, eliminating the false positives, et cetera. And then ultimately you get to the field trials, which is even more time consuming. The primary challenges for us in the implementation and for our customers was, as you could expect, a rear camera is quite small. So the module being small, placed some really tough constraints on the design. In addition, in this case, the module has to be watertight and airtight, which means there's virtually no airflow. Huge amounts of, you don't actually realize it, but the image sensor actually generates a lot of heat on its own, and then naturally the processor itself will generate a fair bit of heat. In this case, the calculation was that the entire vision processing had to be done once you take everything else out, had to be done with under 500 milliwatts of power. So the heat dissipation became a critical issue, and it became critical as well for, of course, the background noise in the nighttime testing, because the heat generated in the camera affected the sensor noise. The solution for the customer ended up being creating small, you can actually see some examples on our demo table. If you come over and look at the CogniVue table, you'll see some examples of some of the rear camera type designs that the customers worked on, but small PCBs. You have to design so the sensor is kept away from the heat. Metal casing, thermally conductive padding, and then efficient power supply design, passive LDO regulators, et cetera. This is the result, or one of the results actually from one customer. This is actually a prototype version, but this version actually is sitting on the table in the demo room. And it's a 1-inch cube. This particular version used a VGA camera, 180-degree fisheye lens, but it did everything. It was one that was put into field trials, and it did pumped out analog video, NTSC, did all the overlay, face detection, tracking, distance estimation, perspective correction, and it was controlled through a GPO line. So the driver just had to click a button to scroll through the different views. By the way, one of the things I'm not talking about here is the calibration issue, which is also very important. Calibration turned out to be a big challenge too. So the lessons we learned, and this seems rudimentary, but for an R&D center becoming a product-based business company, delivering robust technology to our customers, it was important, of course, to have programming guidelines for our developers to reduce the number of rewrites we had along the way in terms of developing that code and delivering it to customers. We ended up discovering ourselves that what our customers ultimately needed, which is what we discovered we needed in the process of getting the algorithm developed, was a vision-centric software framework. This has actually resulted in a product we call the Apex Core framework, which actually pipelines the vision kernels efficiently on the platform. And it eliminates a lot of heartache and headache trying to optimize for your platform. So vision-centric software framework, not just a vision processor. And then, of course, specialized vision libraries are useful. I think everybody realizes that. Coming up with optimized vision kernels, for instance, and primitives that you can use. Number 4, I mentioned just briefly the calibration of the camera when you're using a camera for distance estimation, calibration is key. And in this case, you're looking at trying to do a camera installation that's simple and low cost when the installer's putting it on the camera or on the car. So the calibration technique actually turned out to be quite a bit of work. There's a calibration initially in terms of creating the intrinsic data for the particular sensor-lenser combination. So we ended up coming up with a tool for that called the PC Lookup Table Toolkit. It makes the task of writing your lookup tables for the de-warping the image really easy and fast. That was one. And that's actually a product now that we sell to other customers. But the other part is the calibration of the camera when you install it in the car. That's another technique in itself. And then this requirement for a golden image test database turned to be, we underestimated totally the amount of work involved in doing that, thinking that we had a robust algorithm at the beginning and not really having that. And part of that came from not having a sufficiently robust test database to work from. So spending a lot of time up front on that test database is really important. And in fact, demanding it from your customers. If you're the CogniVue, helping your customer get the product out, the requirements document should include actually the test database that you should be validating against. That they say, okay, if you pass all these test videos, you're done. That should be there. We didn't have that at the beginning, and it turned out to be it was definitely an issue for most of our customers because it was difficult to decide when you were really finished. And then you've got a plan to do many iterations because vision's not an exact science. Every object is different depending on the environment you're in. It may look like a person in one scenario and not a person in another, and so on. So that ends up always, you totally underestimate this side of what you do. Many iterations to actually make it work robustly. Now a little bit about our sort of view on the market then. And I think it's borne out through our experiences with our customers that, there was the 1980s was the year of the CPU, where CPUs got introduced as cores you put into SoCs. Programmable DSPs came in the 90s. That was my background, actually. Worked at TI and developed the first 64X DSPs. They were really designed for solving the audio and communications signal processing problem. And they evolved from there, but that was the focus of the DSP architecture. And then the last decade was the decade when GPUs were introduced. With NVIDIA, Imagination Technologies, ARM, Mali, and so on, Vivante. It's designed for solving the 2D, 3D graphics processor problem efficiently. And we believe, and I don't know if ICP is the term, but it's going to be some sort of acronym, will describe the necessity of having a vision processor core in your chips. And you can see it if you go to the floor. You'll find a number of companies actually now promoting. We felt like evangelists maybe three years ago, but today you have CEVA out there with a DSP and vision acceleration. You have Tensilica made announcements about their IVP. They call it IVP. But essentially it's an image cognition processor core. And there's some other companies as well now recognizing the necessity for a vision core to really do embedded vision processing efficiently. Efficiently meaning power effectively, cost effectively, and so on. And we believe actually compared to the conventional cores, it's about a 10 to 100x improvement that's really needed in the market. And that's what, if you see the advertisements from some of the companies out there, that's really what they're calling on when they compare against, let's say, Cortex and so on. And as I described earlier, our lessons learned actually ended up creating the products that we're pitching today. So working with our customers on these challenging vision applications, of course, we have the underlying hardware. You need this big boost, but you also need this middleware software solution to give you the efficient pipelining of the vision kernels to create an overall efficient vision algorithm implemented on your chip. We call this the Apex Core Framework. Probably other companies will come out with something similar to that to help create an efficient pipelined vision algorithm. And then above that, it's just basically helping your customer get to market quicker. So we've, in some cases, productized some of the stuff that we did for our customers as we went along. The rear camera application resulted in a toolkit. So other customers can take that toolkit and build their own rear camera from it without having to reinvent the wheel. And there's some resources. That's our website. OpenVX, which isn't out yet, but you might hear about it later today, I think. Is there going to be a presentation on OpenVX? which is an API for vision. You should check that out. And OpenCL, a heterogeneous programming language. These are other things that CogniVue is also focused on. And OpenCV, you've heard about. Jeff, thank you. Any questions?
We have time for questions. Please raise your hand if you've got a question. We'll bring a mic to you.
Yeah,
Nicely
hi.
done, Simon.
3 questions. Did this module went into production?
Yes.
Was 500 milliwatts your budget for the whole module or just the DSP portion of it?
Just the the ICP portion of it.
And can you comment on what kind of false positive and false negative rates you guys deemed ready for real world applications?
I don't recall, but we had to pass in the field trials with no false positives.
No false positives.
Yes. You don't want, the tests that we went through, you can't, it's okay, actually a false positive might be all right because it's not damaging, but it draws the driver's attention away to the screen. So it's something you still want to avoid anyway, at least minimize it. And in our case, where the tests that we had to pass included no false positives. That being said, there are weather conditions and nighttime conditions where you still get false positives, but we didn't those were considered scenarios where the camera was blind. Okay, so there's a definition of blindness in your product, and you have to make the consumer aware of.
Another question?
Yes. For your next generation of products, where do you see the biggest obstacle in heat dissipation? Is it the processor? Would you need a better sensor? Or do you need better packaging to support your product's requirements?
Well, I would say it's our customer's product requirement, but some applications aren't as challenging as that rear camera one where they wanted to put the processing in that small module. But we see the power issue coming mostly from the processor itself and the data movement. And so we focused heavily on, in the next version of the technology, which we licensed to Freescale recently, that was a big focus of our research efforts, is actually minimizing data movement in the vision algorithm implementation, because that's where the power was going, was at the data movement in the algorithm.
Other questions for Simon? Going twice. All right. Well, Simon, I really enjoyed your presentation, even though I'd seen a similar one in September. I think I learned something new, and I appreciate the lesson learned on if you don't have good testing data, you're sort of nowhere, right? That's your spec, in a sense, is the test data. So that's an essential requirement. And also, I appreciated your comment on the software framework. I think people put a lot of attention on selecting the processor. They think a lot about software component libraries, but often it's an afterthought how it's all going to get tied together, right? And that plumbing is just as important as all of the other pieces. So really great to have this sort of lessons from the trenches, so to speak. Thank you very much for the excellent presentation.